Well, in the last class, we told you that in this course we are going to study the structure property relationship in materials which are used by the engineers in the practice of their profession. And then before we started talking about the structures of materials, we said that we shall look into the certain aspects of equilibrium and kinetics in materials, which we shall be using time and again. While discussing that, we talked about the internal intensive properties of materials like pressure and temperature. Then extensive properties, that's what we are talking about, internal energy, enthalpy. And towards the end I was telling that if this energy is to be considered for the stability of a material, it doesn't match with our common experience. Like above the melting point, it is the water which is stable, not ice, and the enthalpy or the internal energy of water is more than that of ice. So that stability criterion is what we have to look at. Shall start from there. The material has certain internal configuration, and to that configuration certain energy is involved which is called the bound energy. That energy is bound to the system and that configuration of the material. It is not available for material to do any kind of work. This bound energy is also called the entropy factor, and we write as T is the temperature in absolute and S is the entropy. Entropy you have studied in school, what's called the thermal entropy, and is defined as we define the entropy as integral of 0 to T Cp by T dt. If you compare this with the other properties we defined, internal energy and enthalpy, there is no constant term here. Means entropy at 0 Kelvin is 0. This is by and large true for what we call the thermal entropy of materials, whether they are solids or liquids or gases, the three states of matter. But when we come to solids, which could be of two kinds, crystalline and non-crystalline, in the non-crystalline we shall be materials we see the structures are similar to that of liquids. But in case of crystalline structures, which we are going to study in this course, shall see the atoms have regular arrangement, periodically repeating pattern is there. Means there are certain set configurations possible in the crystalline solid. That also gives rise to the entropy. Before I come to talk about that, difference between solids and the other two states of the matter, liquids and gases. There are three kinds of motion any atom can have. One is the oscillatory motion, second one is rotational, and third is translation. In the case of solids, starting from 0 Kelvin and up, this is the only motion available. At 0 Kelvin, of course, there is no motion available. Oscillatory motion is the only motion available to atoms in the solid state. Only when they are about to reach the melting point that some rotational motion also begins. Otherwise, that is not the characteristic of solids. While liquids and gases can be characterized by the rotational motion and the translation motion. In other words, these two motions are not there in my solids. So therefore, atoms in the crystalline solid are oscillating about their mean position, what I call a fixed position of the atom in the solid or the crystal, and they are oscillating with varying amplitude and varying direction. However, starting from 0 Kelvin, even the frequency begins to increase, because at 0 Kelvin everything is 0, you can say the frequency is 0. It begins to rise, and by the time it reaches about 200 Kelvin, that this frequency stabilizes, and we call this frequency the lattice vibration frequency. And this lattice vibration frequency is 10 to the power 13 per second at temperatures which exceeds about 200 Kelvin, and remains constant at that. Most materials we are using at temperatures higher than 200 Kelvin, so we shall use this as the lattice vibration frequency for all our studies this course. This is about 10 to the power 13 per second. Okay. Alright, this oscillatory energy which is available to the atoms in the crystalline solids or non-crystalline solids, also atoms are oscillating about their position, but there is no regular arrangement in case of non-crystalline solids. This is referred to as the thermal energy, and defined as average energy per atom per mode of oscillation we defined as K into temperature in absolute, where K is the Boltzmann constant. Well, it is slightly different from what you studied in gases, studied about 3 by 2 kT, okay, and Boltzmann constant K is 1.38 10 to the power minus 23 joule per Kelvin. This Boltzmann constant, once multiplied by another constant, what is called the Avogadro's number, which is quantity of 1 mole, becomes the universal gas constant, which is equal to 1 K into N0, and that's equal to 8.314 joule. Now, since we are multiplied by this Avogadro number N0, we express it per mole per Kelvin. Why I am saying this is because this interchangeable use of K and R would be coming in this course, and you have to be aware about it. Alright. Now, since we talked about the thermal energy, you have also studied maybe that entropy measures randomness in materials. What randomness does it measure? Talk about the thermal entropy. I have just said atoms are oscillating about their mean position. Their amplitude of oscillation is varying, the direction of oscillation is varying. Now, in the process what happens is the two neighbors at times may collide. During the collision, one can transfer the energy to the other, and thereby one can gain the energy, other can lose the energy. In other words, these amplitudes could be varying from 0 to very high, and directions can also get changed during collisions. So, randomness therefore is in the direction as well as the amplitude, and amplitude is a measure of the energy. Therefore, atoms do not have the same energy, which are oscillating about their mean position. The one which has a higher amplitude has a higher energy, the one which has a lower amplitude has a lower energy. So, energy is varying from a very small value to a large value. And when I talk about the crystals, even a crystal of the size 1 centimeter by 1 centimeter by 1 centimeter may have of the order of 10 to the power 23 atoms in it. So, I am talking about a very large ensemble of atoms, where every atom is having random amplitude and random direction of oscillation. So, this randomness associated is in the direction So, randomness associated with the thermal entropy is in the direction of oscillation and amplitude of oscillation. Since it is an ensemble of very large number of atoms, we can talk of statistics, we can talk of an average energy, we can talk of energy greater than a particular value and things like that. You have also seen the Maxwell-Boltzmann statistics in case of gases earlier. This statistics we use, besides we will be using another statistics which we will talk about later, quite similar to this. But what the Maxwell-Boltzmann statistic says, in an ensemble where the energies are varying from a small value to a large value, and this keeps varying at the same time when they are colliding, change of energy is taking place. The probability that in an ensemble a species has an energy greater than or equal to a given value E at the given temperature T is given by a number exponential of minus E by kT. This probability, when I add up for all the atoms and then divided by the total number of atoms available, shall give me the fraction of atoms which have the energy greater than or equal to the value E. So, this is also equal to fraction of species at temperature T. Now, having looked at this thermal entropy and the randomness this measures, we shall look at the another kind of entropy which does not exist in liquids and gases. It exists only in crystalline solids, not even in non-crystalline solids, because we are talking about certain arrangements which are called the configurations of atoms in the given space, which is the crystal. And let us say I have W as the number of configurations of the same energy, then it is possible for me to define configurational entropy in solids as Boltzmann constant times natural logarithm of W, where W is the number of configurations having the same energy. Now, just to look at this, I take here a model containing merely 16 atoms. 8 atoms of the green kind, other 8 atoms of the red kind. I have tried to arrange them in 4 possible ways here. And out of these, you can see these, the arrangements where here green is neighbor to in here we see that the this red is surrounded by green here, green there, green there. That means you can say, let us say, it's a A atom, this is a B atom, the AB bond. This is also an AB bond, this is also an AB bond, this is also an AB bond. But in here we find this is a AA bond, and here we find again this is an AA bond, again AB bond, like here we have BB bond, and so on and so forth. Same is true about the second arrangement here. There are AA bonds, BB bonds and AB bonds. But the other two arrangements which I am showing here, see, there are only AB bonds, there is no AA bond, there is no BB bond. Look at here, I have only AA bonds and BB bonds. This is just an interface here, but on this side this is all AA bonds, on the right side they are all BB bonds. There are no AB bonds here, while there are no AA bonds and BB bonds here. This and these two arrangements probably do not have the same energy as compared to the other two, where the locations for A and B are randomly decided. But if I look at how many arrangements do I have, then it's possible for me to work out the W as 16C8, which can be written as 16 factorial divided by 16 minus 8 factorial multiplied by 8 factorial. You can simplify this, you will see that 16 to 14 to 13, 12, 11, 10, 9 divided by 8, 7, 6, 5. It's very easy to simplify this. 8 into 2 cancel with 16, and let's say 6 cancel with 12, 7 cancel with 14, then I have 5 into 3 cancels with 15, and I am left with 4. This 2 and 2 will cancel with this 4. I am left with 13, 11, 10 and 9. That makes it 11 into 9, 99. So that is 13 into 9, 90. And that should be not difficult to work out, should be. There are 12,870 arrangements possible, out of which only 2 are the kinds where I have only AB bonds or I have AA bonds and BB bonds. Those are called the ordered arrangements. There are only 2 ordered arrangements, while rest of them are all random arrangements. So I can neglect 2 here, it will not affect me when I work out the natural logarithm of this number. But once I have 10 to the power 23 atoms and I try to work out this number W, it becomes a very large number, and then subtraction of 2 is just no problem, and we can do that approximation, right. So while talking about the W, strictly it is a number of configurations of the same energy, but I have shown you that some are having more energy, some are having less energy, and the arrangements which have different energy are only 2, like in this case of with 2 atoms. If I have more atoms, I could have more kind of configurations of that kind.
Why the 2 which we are leaving have different energies, and then which we have left?
Yes, this is a very good question. AA bond doesn't have the same energy as the AB bond. BB bond doesn't have the same energy as the AA bond. So all 3 bonds have different energies. Where I have an ensemble only AB bonds, I have 1 energy. Where I have AA bonds is 1 energy. Where I have only BB bonds, another. So this energy is going to be different of the ensemble, right? Right. Coming back to this, where we wrote this entropy as W is going to be very large number times and factorial of 10 to the power 23. So normally we use Stirling's approximation to simplify that, which says logarithm of x factorial is x log x minus x, provided x is greater than 1. So that's Stirling's approximation we make use of to simplify this number. So now we have seen the entropy of two kinds. One, the thermal entropy, that's my problem. Talked about thermal entropy and the configurational entropy. So my solid is going to have the thermal entropy as well as the configuration entropy. Means thermal entropy is temperature dependent, configuration entropy is temperature independent. It regards the configurations of atoms, it does nothing to do with the temperature. So this is temperature dependent and this is temperature independent. Now this sum of the two entropies is the entropy of microcrystalline solid, and the bound energy is therefore, which is T into S, is bound to the configuration of the system, and therefore from my enthalpy or the the internal energy, if I subtract this, it becomes my free energy. Free energy is the total energy and bound energy is the entropy factor. So we define it two ways. One is the Gibbs free energy, which I just said is G is enthalpy minus the bound energy, and Helmholtz free energy we define as E is equal to U minus Ts. In case of solids, I already said that PV term is negligible. So difference between the internal energy and enthalpy is negligible. So for us, Gibbs free energy and Helmholtz free energy are also almost same, and therefore we use them interchangeably as and when required. Okay. So for us in solids, all right, yes please.
In Maxwell-Boltzmann study, we define the fraction as exponential of minus E by RT. Then that
E by KT I said.
E by KT. That E is what?
Is the energy of the species you are talking about. It's oscillating. So what is that energy with which it is oscillating? That's the energy we are referring to. Okay. Right. Now here I have free energy. That's my problem. I think it's my problem. in the case of enthalpy, we saw that enthalpy of the solid starting from 0 Kelvin rises as the temperature rises. At the melting point, the solid material absorbs the latent heat of fusion. Beyond that, again the liquid, again the enthalpy increases. But in case of free energy, the free energy continues to decrease with increasing temperature. There is a problem which we are going to work out, which says that the slope of this curve is nothing but minus of entropy, and entropy at 0 Kelvin is 0. So therefore you see the slope of this curve is 0, and this keeps on rising as the temperature rises, but the sign is negative, so slope of this curve keeps on increasing with rising temperature. That's for one state of the matter. Similarly, for the second state of matter, I have the second curve. So let's say this is for the solid and that's for the liquid. And now you can see that it's the free energy of the solid. Here is the melting point. Below the melting point is lower, and above the melting point is the free energy of the liquid, which is lower, and therefore there is a stable state of the material. So I can use for stability criterion the free energy of the material. Okay. Comparing with what we talked about, the rectangular block where we discussed the potential energy, now we are talking about the free energy, right? And therefore we can say that material would be in its stable state if its free energy is at its minimum. If it is a global minimum, it is the most stable state of the material, and if it is simply a local minimum, it is a metastable state of the material. And metastable state, as I said, is very important. For most materials what we use are there in their metastable state. For example, majority of the materials may be available as oxide in the most stable state at room temperature, but the steel which we use, steel bridges, they stand there for 100 years, 150 years. Steel has stayed there for 150 years without oxidizing, though we have taken care of it. So for all practical purposes, that is a stable state of the material, and that's why we are worried about the metastable state. So which state, the free energy is the minimum, a local minimum is not a metastable state, global minimum is the most stable state. So the stability criterion is going to be a minimum in free energy. G is the Gibbs free energy, E is the Helmholtz free energy. Okay. Now, if I take a block of ice and keep it at room temperature, which is above the melting point of the ice, means I am somewhere here, I'd have to do nothing, it will keep on melting by itself. Such a process is called spontaneous process. And if a process is spontaneous, the change in free energy associated with it must be negative. The change is always defined as G in the final state and G in the initial state. But it is not always true that if the free energy change of a process is negative, it's less than 0, the process would be spontaneous. On the other hand, if it is a process taking place spontaneously, like the example I took, keep a block of ice here, it will keep melting by itself. The change in free energy has to be negative. So that's all about the stability. And if I go back to the rectangular block, we consider its potential energy, because there was no change in its entropy. Whether I keep the block vertically up or horizontally down, its entropy doesn't change. So I could talk about its potential energy, which you can say is the change in the energy of the system. That's the only change which was taking place. Otherwise, I should always talk about the free energy of the system if I am looking at the stability. Next, coming to kinetics, which also you have done in the school, particularly you have done the this you have seen with the help of Arrhenius plot, which he in a kind of a reaction like hydrogen combining with iodine to form hydrogen iodide. Studying the rate of the process, Arrhenius found a plot like this, which when plotted against the reciprocal of the temperature in absolute, found a straight line with a negative slope. If this slope is given as the value usually minus q by r, this logarithmic relationship can be written as logarithm of rate is equal to some constant minus q by RT, or you can rewrite this to put it in terms of exponential form. Rate is equal to some constant, let us call it A 0 times exponential of minus q by RT. A and A0 are related, you can see that. So this is what you have seen in the school, the Arrhenius plot. We shall try to rationalize this. Let us consider a process where species A and BC combine or react to form the product AB and C. If you look at this product formation, BC, the bond B and C must break. Bond between B and C must break, and a bond between A and B should form. That kind of a process is to take place. All BCs must break their bonds, and then all A's should go to the B and get attracted to B to form the bond. Looks a little improbable thing to happen when you have species of the order of 10 to the power 23. But rather what seems to be possible is A and BC, because these species have energies varying because they are all oscillating about their mean positions. Their energies are varying. Some of them have very high energy. When you have high energy, you can do many things, and it's possible for it to form a very high energy complex. ABC, they are all together. And this ABC complex also oscillates like any other atom, A or BC, or molecule, or let's say AB molecule. They keep oscillating. And during oscillation it is possible that they split. It can split back to become A and BC, or it can split to become A, B and C. So if it splits to become A, B and C, the reaction goes forward, or it comes back. This possibility is there, probability is there. Probability is not zero for it going back. But this looks a little probable, because some species will have very high energy, a high energy complex can form. This is called an activated complex. And this activation or this extra energy is provided by the thermal energy. We know that they are oscillating, and this is varying from a zero value to a very high value. This energy I have shown here. For the reactants, this is the average energy here at this level. This is the average energy of the reactants. Average energy does not mean that every species shall have that energy. Some will have less than that, some will have more than that. And as I said, KT is the average energy, but energy can be very large, very high too. And this is the activated complex. All species of these A and BC which can have energy greater than this are in position to form this kind of a complex. Energy should be greater than this. Let's call it delta H star. It could be great. Once it is greater than this, it is possible to form this complex. Once this complex, as I said, is formed, it is oscillating. It can go back or it can go forward. While going back, it goes to a little higher energy. When it goes here, it's a little lower energy. It's going forward because this is a lower free energy state. So average energy is also lower there. So more chances of it's going there and less chances of going there. So net is it's going there. This is what, if we consider, then the only thing we have to make an assumption that these A and BC is all the time in thermal equilibrium. Once they are in thermal equilibrium, my Maxwell-Boltzmann statistics will keep working, keep telling me that there is a fraction which has energy greater than this, and that complex is always there. It is all the time available for it to split to go to the product side. Though it is a very small fraction, we will see that, but this small fraction is taking the reaction forward, right. So we can try to rationalize this with the help of this knowledge. And say the rate is proportional to, that is, the species which have energy greater than delta H star. All right. And once they have these species which are complex, activated complex, they are oscillating and oscillating with the lattice vibration frequency. So the rate is the vibrational frequency, because in one oscillation it can either go to the product side or it can go back. So it's only that rate at which is going on. The fraction which have energy greater than or equal to delta H star, we know from the Maxwell-Boltzmann statistics, then small n would be the total number of species which I have times exponential of minus delta H star by KT times nu, or you can write this as n times nu exponential of you can say that this with the proportionality constant will form the pre-exponential term, what you saw, that A in the Arrhenius relationship, and this forms the exponential term. The difference only is in there we are use Q by RT, and here I have delta H star by KT. Now if I multiply this numerator by N0, the Avogadro number, and denominator also by N0, the number remains the same, but N0 into K becomes R and delta H star into N0 becomes Q. Why we normally do this is handling of numbers. Delta H star is in the range of 1 electron volt. That means 1.6 10 to the power minus 19 joules. But when I multiply this by Avogadro number, it comes in the range of 6 kilojoules. Right? It is in the range of kilojoules now, and I call it kilojoules per mole. A number becomes handy, and it is not 10 to the power minus 19 which I have to work with, and similarly the denominator also is multiplied by this, and K, the Boltzmann constant, becomes a gas constant. So this Q by RT what we use and the delta H star by KT are the same numbers, they are not different. This will be coming in this course again and again, that is what I said, and you should be aware of it. Well, this for the use of Maxwell-Boltzmann statistics in rationalizing the Arrhenius relationship which we have studied, and we shall see some more details, more refinement in solids than what we have done in right. So what I have talked about so far is the extensive property like internal energy, extensive property like enthalpy. For solids they are both same, not different. Then I talked about in solids the entropy. There are two kinds, one is thermal entropy, another one is the configurational entropy. Thermal entropy is what you have studied in school also, and definition remains the same. Configuration entropy works only for the crystalline solids and not even for non-crystalline solids where there are no configurations. Again, configurational entropy, like the thermal entropy, cannot be negative, the minimum value can be 0 because of the definition. If you recall, K log W, the minimum value of W can be 1. Like it is a situation in an ordered solid when I can have only AB bonds, absolutely ordered solid, no other bond, no AA, no BB. A is surrounded by B, B is surrounded by A, it is an ordered one, there is only one arrangement. For such a configuration, the configuration entropy is 0. Okay. So that is about the entropy, which also gives rise to the bound energy in the system. This energy is bound to the system, not available. So that has to be subtracted from the energy available, internal energy, enthalpy, the total energy. Once it is subtracted, I get the free energy. And free energy is the one which we use as a criterion for stability, and it should be a minimum. And a minimum on free energy is the criterion for stability. Then we also talked about the Maxwell-Boltzmann statistics, which gives us the probability of any species having energy greater than or equal to E, or for that matter the fraction of species having energy greater than or equal to E in a given ensemble where I have large number of, this is exponential minus E by KT. Then we have also talked about the thermal energy, average thermal energy in a crystalline solid. As I said, since the atoms are oscillating about the mean position, for that matter even in the non-crystalline solid atoms do oscillate about their mean position, and that is the average thermal energy is kT. Now I talked about certain processes for working out the kinetics, the rate of a reaction, where thermal energy is helping the process to go forward. In what way? It's the thermal energy which is allowing a complex to form, because during oscillations species are colliding, changing the energy, some energies are becoming higher, and it's possible for an activation complex or activated complex to form, and it is this which can split to form the product. So such processes where thermal energy helps the process go forward are called thermally activated processes, right? And then we saw the Arrhenius relationship, where rate is defined as some constant times exponential of minus q by RT. And it is for the thermally activated process, mind it, because the way we have tried to explain this, I need to form a thermally activated complex, and therefore the thermal energy is helping the process, and that is a rate for a thermally activated process, right? So with this we end this introduction on equilibrium and kinetics. In the next class on we shall start with the crystal structures.